Chapter 3.2 exercises 21 through 22 and 29 through 34. This section of the book, section 3.2, has to do with exponential and logistic modeling. And we're going to look at the odd number problems here. In exercise 21 through 22, determine a formula for the exponential function whose graph is shown in the figure. Exponential functions have their basic format like this. So we're going to have a function. We'll say we have an x and y coordinate plane. So we'll say f of x is equal to our initial value, which I'm going to call v sub 0, times our base to the power of our variable, which is x. And so I'm going to just label this here. I'm watching. And v sub 0 we call initial value. And this b is what we call our base. So to find our initial value, we have to look at what the value of the function is where x equals 0. So we look at our y-intercept. So initial value of an exponential function equals our y-intercept. And we can see, I hope, that based on the 2 points given in this exponential function, this is an exponential growth curve, by the way, let's write this, f of x is equal to our initial value, which is 4, times our base. Now we have to figure out what our base is. Well, to do that, I'm going to go ahead and make a table just to figure out what it is. So we have a table with x and y input values. So for an input of 0, we have an output of 4. And we come all the way down to x equals 5, which I'm going to do down here. We have an output of 8.05. And so to find out what b is, now if we had these 1 unit apart, we would know what b is. We would just take one value above divided by the value below. But here we have not only 0, we have 1, 2, 3, 4, 5. And so some number times 4 is going to equal the output for x equals 1. And then that output is going to be multiplied by that same number again, and then again to get where x equals 3, again to where x equals 4, and again to where x equals 8.05. And so how many times is this base going to be multiplied by itself to get from 4 to 8.05? Well, the answer is 5 times. So what we can say is that b times itself 5 times, or to the power of 5, is going to be equal to our ratio, our final value, which is 8.05, over our initial value, which is 4. And so, again, to kind of work out below, I'm going to put b to the 5th down here, just to leave room for the operation. B to the 5th equals 8.05 over 4. And what do we do to isolate b, to get b by itself? Well, we take the 5th root. And when we take the 5th root, that cancels out to the 5th power. But on the right side, using the golden rule of algebra, we need to do the same thing. So we take the 5th root here to this fraction 8.05 over 4. So we get b equals the 5th root of 8.05 over 4. And to find out what that is, we can resort to our calculator. So I'm going to press Control Exponent. We'll put 5th root here and go inside the radical and put the fraction there and put 8.05 over 4. And we're going to get our value for b, which is 1.15013. 1.15013. So that's going to go in the place of our equation up here. So we're going to put this up here, for B. And so I'm going to put in 1.15. That's how the book rounded it. And so we would say f of x or y equals 1.4 times 1.15 to the power of x. And so we're going to box that in as our correct answer. We could put y equals also, that would have been fine. Next item of problem, which is 29, exponential growth. The 2000 population of Jacksonville, Florida was 736,000 and was increasing at the rate of 1.49% each year. At that rate, when will the population be 1 million? And so for this, we have a similar type of equation as we did for problem number 21, and that is population equals our starting population. And for that, what I'm going to do is I'm going to call, instead of big P, I'm going to call it P sub t. In other words, we're going to make a function notation where we input the value of t to this part on the right for the independent variable. So P sub 0 is our starting population, and then we have times quantity 1 plus R, and R is our rate to the power of t, and t is our variable. And rate is related to this 1.49%, so R equals 1.49%. And that's a percent version, and to convert this percentage version to a decimal version, which we're going to need for the formula, we take, we're going to get 1.49 divided by 100, or move decimal places to the left, we're going to get 0.0149. And so just simplifying, we have P sub t equals P sub 0 times 1.0149 to the power of t, and we're going to go ahead and put in numbers for these. P sub t, we're interested in our final population being 1 million. So I'm going to put in 1,000 equals 736 times 1.0149 to the power of t. Now, where did I get 736 when this thing says 736,000? Well, the reason I got this because I'm a little bit lazy. I didn't want to write as many zeros, because I know that the ratio of 736,000 to 1 million is the same as 736 to 1,000. And it's going to be readily apparent when we solve for t. And so let's go ahead about solving for t. And we're going to try to get t by itself. And we have t over here with this 1.0149. But if we divide both sides of this equation by 736, we have a cancellation on the right. We get 1.0149 to the power of t equals this fraction 1,000 over 736. Now, what can we do to get t by itself? Well, we can, when you have a variable as an exponent, you want to solve an equation, we can rewrite this function here, exponential function, as a logarithmic equation. And to do that, the base of our logarithm, I'm going to write log, the base of our logarithm here is going to be the same as the base of the exponent. So I'm going to put log base 1.0149 and of this number here on the right, which is the fraction 1,000 over 736, is going to be equal to our unknown t. So if we go into our calculator, we get our logarithm by pressing Control log, and for this we're going to put 1.0149 and of which value, control division, we're going to put 1,000 divided by 736. And we do that, we get 20.725. So T equals 20.725 years. And to find our year, at what rate, now this is the amount of time, we're going to have the year 2000 plus this value 20.725. And so when we add these together, we get 20.725. So that will be the year. And let's see how we're at. So that rate, when will the population be 21 million? Well, it's going to be just before the year 2021. So we said, we'll say by the year 2021. And one way we could do this is we could graph this function right here. See this p sub t equals p sub 0, or this 1,000 equals, we could enter this 736 times 1.0149 to the power of x. So let's go do that. We go to our, this time we're going to get a graph. There's a graph. So we're going to put in the function 736 times 1.0149 to the power of x. And we graph the function. We can't see it. The y-intercept is going to be way up here. But it's going to be at 736, right? But if we go to our table view, we press Control T, we're able to scroll down. And if we scroll down to year 20, because we're talking about 2020, well, we can see at year 20, we're just below 1,000. At year 21, we're just above 1,000. So at nearly year 21, we're gonna meet the conditions. So that corresponds and corroborates our answer here by the year 2021. Next on the problem, which is 31, another exponential growth. The population of the town Smallville in the year 1890 was 6,250. Assume the population increased at a rate of 2.75% per year. So let's go ahead and look at that. As far as an equation goes, it's going to look something like this. Our population, which we're going to call P sub t like we did in the other one, is going to be equal to our starting amount, which is 6,250, times, we're going to have so our rate, our base is going to be, equal to 1 plus our rate, which equals 1 plus 0.0275, which equals 1.0275. So we put this 1.0275 to the power of t. And for when the population in 1915 versus in 1914, well, we have to look to plug into this equation what t is. So for problem, this is problem A. So for problem A for 1915, we're going to plug in the years, the difference of years between 1915 and the initial time, which is 1890, and that's going to be 25 years. And then similarly, for 1940, we're going to take 1940 and subtract out 1890, and how many years was that? 50 years. So we're going to say P sub, and the time is going to be what we're going to look for, 1915, is going to be equal to this 6,250 times 1.0275 0.0275 to the power of 25. And also, P and population of the year 1940 is going to be equal to 6250 times 1.0275 to the power of 50. So let's go to our calculator and figure out what these are. Now we'll do a Control I and do that. We'll get a calculator page. We're going to put 6250 times 1.0275 to the power of, we're going to use, let me get the right thing here, to the power of 25. So we're going to have 12,315, it looks like, for that value. So I'm going to put in P, so 1915 equals 12,315. Okay. And then P of 1940 is going to be equal to, okay, we go to our calculator again, same thing. And let's see, can we do this? Let's do 6250 times 1.0275 to the power of 50. We're going to get how many people? Population of 24,265. So these would be our answers to part A. Now to part B, predict when the population reached 50,000. So for part B, that's part A. Part B is going to be 50,000 equals 6250 times 1.0275 to the power of t. And for this, I'm going to use a technique in the calculator that's called numerical solve. And a lot of these calculators have that. Instead of doing the logarithm like we did on that earlier problem 29, I'll just show you how this works on the calculator. Okay, we go to menu and we go to algebra and then numerical solve. And so 50,000 is the population that we're targeting, and that's going to be equal to 6250 times 1.0275 to the power of our variable x, our unknown x rather. And then we go down and press comma and x. And we get 76.65 years. So t equals 76.65 years. And so we're being asked to predict when the population reached 50,000. So for that, we're going to take 1890, our starting year, plus 76.65 years, and that's going to be equal to 1966.65. So we're going to use that to answer. We'll say during the year 1966. That'll be later in that year. So that'll be our answer to part B in problem 31. Next odd number problem, which is 33, radioactive decay. The half-life of a certain radioactive substance is 14 days. There are 6.5 grams initially. Express the amount of substance remaining as a function of time, t. Well, in the half-life formula is going to be amount equals our starting amount, a sub 0, times our base. And in a half-life formula, our base is going to be 1/2 to the power of our time over our half-life. So that's the basic formula. So for this, express the amount of substance as a function of time, we're going to say amount as a function of time, so we'll call it a sub t, is equal to, well, we have 6.6 grams initially, so we say a sub t equals 6.6 times 1/2 to the power of t over our half-life, and our half-life of the substance is 14 days, so it's going to be t over 14. So t over 14 is an exponent's place. So that's really it. That is our answer to problem number 33, part A. Okay, part B, when will there be less than 1 gram remaining? So for that, we use the same equation developed above, but we take, in place of a sub t, we put 1 gram remaining. I'll put b here to the side. 1 is equal to 6.6 times 1/2 to the power of t over 14. Now in this case, our unknown is t. Well, we can solve this by dividing by 1 divided by 6.6, right? So, I don't know, that's just, I'm going to be lazy and go to the end solve again. And I'm going to go to numerical solve, and that's algebra 3, option 1. So we have 1 gram is equal to our starting amount, which is 6.6 grams, times our base, which is 0.5, which is for half-life, and we have to the power of, we're going to put control division, we're going to put x over 14. And then we're going to put comma, I hope this works, and x. Press enter. We get 38.1145 days. So t equals 38.1145 days. And that's when we're going to start. So during day, early in the day, 38. So it's beginning. Anyway, those are the answers to our problems here, or odd number problems. Good luck with your even number problems, and thanks for viewing.